In this video, we're going to talk about rotational kinetic energy and rotational inertia. So let's start with saying we have an object, maybe shaped like this, and it is fastened right here, and it rotates around at some angle, at some angular velocity, omega. Okay. Now let's consider what the kinetic energy of this would be. So let's consider maybe a couple of points. Let's say I have a point right here with some mass. We'll say this is infinitely small, and this is just mass A. And I'll have another point over here. Maybe this is point B, and it has a mass of B. Not necessarily the same as the mass of A. And then we have another one over here. Let's say this is point C, and it has some mass, MC. And these are all located some distance from the axis of rotation. So I'll say this is our distance to C. This is RC. And then we have the distance to B. I will call this RB. And I will call this distance to A RA. So they all have some distances there. And so then there is some linear velocity or tangential velocity associated with all of these points at their, at the snapshot in time when it's rotating like this. So then there's some tangential velocity. There's some tangential velocity here. We'll call this VA. And there's some tangential velocity here. We'll call this VB. And there's also a tangential velocity here. We'll call this VC. Now, the linear kinetic energy of each of these points, remember that kinetic energy is 1/2 mass times the velocity squared, or really just the speed squared. Once you squared the velocity, it lost its directionality, right? So the kinetic energy at point A would be 1/2 the mass of point A times the velocity of A squared. So this is the times the velocity of A squared. And the kinetic energy at point B would be, kind of following the same reasoning here, this would be 1/2 the mass of point B times the velocity at B squared, and so on for C, etc. So the kinetic energy of the entire thing that's rotating would be the sum of all the kinetic energies of all these points, right? I could break this up and we can have an infinite number of points. So the whole kinetic energy of this entire thing, as it rotates around, so this would be our rotational kinetic energy, will be 1/2 the mass of A times the speed of A squared plus 1/2 mass of B times the speed of B squared plus 1/2 mass of C times the speed of C squared plus yada yada yada. We could have an infinite number of points here. Of course, then we know that the linear speed or tangential speed was equal to the radius times the angular speed, right? And if this is a rigid body, all of these have the same angular speed, omega. So I can replace this here. They have different radiuses, radii, but they have the same angular velocity. So our rotational kinetic energy is equal to 1/2 mass of A times RA omega squared, right? This would be our linear velocity at point A, RA omega, right? And then plus we have 1/2 mass of B times RB omega squared plus 1/2 mass of C, RC omega squared. And so we have a 1/2 an omega in every one of these, right? Actually an omega squared. So the next line here, I'll factor all this out. So this is going to be 1/2 omega squared times, we have here MARA squared plus MBRB squared plus MCRC squared plus yada yada yada, however many points we have. Okay, so that was just factoring out that omega squared from all of these. So this is what we call, so the sum of mass times distance away, I see I have the same thing for all these. Mass A times distance to A squared plus mass B times distance to B squared, mass C times distance to C squared, etc. This is what we call rotational inertia. So our rotational inertia is this. Or sometimes this is called moment of inertia, because back when we talked about sometimes the torque is called a moment, so this is sometimes called the moment of inertia or rotational inertia. And so what it is, we symbolize it by I. I is the sum of all the masses times how far away they are squared. And we say from I equal to 1 all the way up into however many points we have. This could be up to infinity. So the mass of each individual point times how far away that point is squared. Now, depending on the shape, this could be very tedious to break this up into an infinite number of little pieces, or even 20 or 30 little pieces. So we have a table we'll show in a moment that is the kind of the result of some calculus techniques. But the moment of inertia, the definition of it is the sum of the mass times the distance away squared. If I only had one point, this would be very easy to calculate. If I had maybe just this one mass over here, let's say this is a point mass, so it doesn't really occupy any space, it's just some distance, and let's say that somehow it's attached by a infinitely thin and massless rope here, or a rod, and it rotates around like that, then this would have the moment of inertia of this mass here would simply be just m times how far away it is. This is r, this distance, so just mr squared, because we just have the one point. But if we have more complex shapes, then we need techniques from calculus to determine what that is. So taking this and replacing, going back to our kinetic energy of rotation, our rotational kinetic energy, this is 1/2 omega squared times this I, this rotational inertia, which is equal to, if we usually write it here, 1/2 I omega squared. So if you remember back to when we first defined kinetic energy, we said that kinetic energy was equal to 1/2 mv squared. Well, we define mass as really an object's resistance to a change in motion. This is what we quantified, inertia. So mass is actually inertia. This is our linear inertia. So this is a linear inertia. But now that we're talking about rotational motion, we use a rotational inertia. So inertia typically just refers to linear inertia, and we say rotational inertia to differentiate between the two. So it becomes, again, like we've seen previously, where we had, delta x becoming a delta theta. We have the same thing here going on. The mass is becoming replaced by rotational inertia, and the equation looks strikingly similar. We have linear kinetic energy was 1/2 times the mass times the linear velocity squared. Rotational kinetic energy is 1/2 times your rotational inertia, or sometimes this is referred to as rotational mass. You could also rotational inertia or rotational mass times the angular velocity squared. So this is your rotational kinetic energy, very, very similar to linear kinetic energy. And like I said, we would get into showing a table of different rotational inertias. So with rotational inertia, we have to be careful. If we go back to how we define it here, if I had this rotating around a different point, let's say it's not rotating around this point, let's say instead we're rotating around this point here, that would affect all of these r's, and that would change its rotational inertia. So the rotational inertia, you have to be very careful with taking a look at what point it's rotating around. If we're rotating around here, all of these r's are different. And there are a lot of them are smaller. So it actually have a smaller rotational inertia around this point than it does around this point. And so that's what this table kind of shows here. The rotational inertia of a hoop, which is a hoop is considered to be infinitely thin, so that it's all of its mass is all of its mass is on the edge, then the rotational inertia of this, I, is equal to just mr squared. So all of its mass is on the edge, and this is when it rotates about an axis through its center. If we have a solid disk, now we have in the next picture down here, if we have a solid disk or a solid cylinder, either one, then some of this mass is distributed at the edge, but some of it is distributed near the center. So we have, just taking a picture of this, in one case, if this is a hoop, all of its mass is located far from the edge, right? So it has a large rotational inertia. But if we have something like a disk, which is solid, then some of its mass is located right here near the center, in which it has the rotational inertia for a piece of mass which is right at the center would be 0, right? Because that distance r away is very small. So if it's no distance away, it has no rotational inertia. And so we see here the rotational inertia of the hoop is larger than that of the solid cylinder because the mass is farther away. Okay, so we actually see here if it's a disk, then it is 1/2 mr squared, and if it is a hoop, it is just mr squared. These would be for the same masses. Again, there's a whole lot of these. I won't go through all of these, but if we have a long rod, a thin rod, being rotated about an axis through the center like this, then the rotational inertia is ml squared over 12, 1/12 ml squared. If we have a solid sphere rotating about any of its diameters, the rotational inertia is 2/5 mr squared. If we have a hoop rotating about a diameter, so this is different than a hoop rotating through its axis, right? So this was one up here at the top. This is one in which it was rotating around an axis through its center. This is one in which it's rotating about an axis through its diameter. So these are different, and this is why you have that hoop is actually 1/2 mr squared if it's rotating about an axis through its diameter. So the axis it's rotating around is very important. Again here, see that when we have this thin rod rotating about an axis through its center, the rotational inertia was 1/12 ml squared, but if you rotate it about an axis through its end, it's 1/3 ml squared. It's much larger if you rotate it about an axis to the end, and this is because we have so much more mass farther away. On average, the mass is all farther away. We have some way out here, which is a very long distance, versus the ends of it are only a short distance here. And remember that the radius is squared. So the farther away you make it, the much larger the rotational inertia is. So yeah, so several other ones given here as well. One interesting thing to look at with rotational inertia, let's say that we have in rotational kinetic energy, is conservation of energy. So let's say that we have a inclined plane here of height h, and we have two choices of things to roll off here, both of the same mass. We have a solid disk and we have a hoop. So say both of these start at rest. Here's the hoop too. So we know the rotational inertia for the hoop is equal to mr squared, and the rotational inertia for the disk is 1/2 mr squared. Which of these would hit if they have the same mass? So they have the same mass and the same radius. So same mass and the same outside radius r. Which of these would hit the ground first? Well, we have to look at more than just mgh, which is how much potential energy they have, and then when they get down here they have kinetic energy. But they have two forms of kinetic energy at the bottom, because not only are they moving down in a linear direction here, but they're also rotating around like this, right? So they're going to be rotating like that. So the total amount of energy they have at the top is their gravitational potential energy, and at the bottom, so this is, I'll write this out more fundamentally, we have here the mechanical energy at the top is equal to the mechanical energy at the bottom. So the mechanical energy at the top is just mgh, and the mechanical energy at the bottom would be their linear kinetic energy, 1/2 mv squared, plus the rotational kinetic energy, which is 1/2 I omega squared, as we just defined a minute ago. Okay, so we have here, if we look at if we want to find out whichever one has the highest linear speed is going to be the one that hits the bottom first. And so we can think back to previously when we defined our linear velocity is equal to our radius times our angular velocity. So this means that our angular velocity is the linear velocity divided by the radius. So we have here mgh is equal to 1/2 mv squared plus 1/2 I v squared over r squared. And we said that they both have the same radius and the same mass, and so we can see here that whichever one has a greater rotational inertia, the greater this rotational inertia is, the more it is going to detract from the linear kinetic energy. So the bigger this is, the smaller this one is, and we want the one with the greatest linear velocity, because that'll be the one that hits the ground first, or hits the bottom first. So we can see that whichever one has a greater rotational inertia, which is going to be the hoop, is actually going to go the slowest. So the disk, which is solid, would actually hit the bottom first. And we can plug in both of these for the rotational inertias and just kind of see. So for the hoop, rotational inertia is mr squared. The disk, it's 1/2 mr squared. So let's look at the hoop first. So for the hoop, we have mgh is equal to 1/2 mv squared plus 1/2. The rotational inertia was mr squared, and then times v squared over r squared. So then, canceling terms, we have the mass is gone in all cases, and the r squared here cancels with the r squared there, and so we just have gh is equal to 1/2 v squared plus another 1/2 v squared, and so this is equal to just a v squared. And so then we have, for the hoop, the speed at the bottom, so we'll say speed of the hoop at the bottom is equal to the square root of gh. If we look at the disk now, then we have mgh is equal to 1/2 mv squared plus 1/2, I in this case was 1/2 mr squared. This is the rotational inertia for a disk. Go back up here, rotational inertia for the disk, and this is just from that table. Rotational inertia for a disk is 1/2 mr squared. And then times, we had here v squared over r squared. And so then again, we have masses canceling, r squared here, canceling with that, r squared there, and we have GH is equal to 1/2 v squared plus 1/4 v squared. So this is equal to 3/4 of v squared. So solving for this, we have our speed of the disk at the bottom would be equal to the square root of 4/3 GH, which is slightly more than just square root of GH. So we see here that the disk would actually be traveling faster than the hoop, and this fundamentally, this comes down to the fact that the hoop has a larger rotational inertia, so it takes more energy to get it rotating, and less energy can be used to slide it down. Lastly, if we just had something sliding, if it were frictionless, then we know that we have mgh is equal to 1/2 mv squared, and this means that the speed would be equal to the square root of 2gh, which would be even larger still. So if it doesn't require any energy to get it rotating, then it would hit the ground even faster still. So there we have it. Rotational inertia is equal to the sum of all the masses times how far away each mass is squared. This is the sum from I equals 1 to infinity, and rotational kinetic energy is equal to 1/2 times the rotational inertia times the rotational velocity squared. This is very similar to 1/2 mv squared.